Good afternoon, everyone. So today we are discussing about the activity coefficients. This is a week 10 session, problem solving session in the course Chemical Engineering Thermodynamics by the course instructor Shashida Goma from IIT Tirupati and Namrata Kulkarni, PMRF scholar from IIT Madras. So, in the last week, what we have understood is what are fugacity and what is fugacity coefficient. So, this all is defined for gas, which is not ideal, and following some other equation of state. And later, we were also talking about what will be the same for a solution. So ideal solution we define, we don't have specifically some equation like PV is equal to RT for the solutions for the liquid phases things. But we take something as a reference which is considered an ideal solution with some properties. So for that, we define it as a similar, like for a gas mixture, we have defined like this, right? That mu I Ig is equal to GIIG plus RT ln Yi. So similarly, here we will have plus RT ln Xi. Okay. This is for the mixture we are talking about. So in the liquid solution. But when we were talking about just a pure species, we were telling about this, right? Fi liquid equals to phi I sat into Pi sat into exponential of VIL P minus Pi sat. Uh, RT, yeah. So this is the pointing factor. And these are derived from POS. Okay, fine. So for the ideal mixture, we define it as this. Okay, similar analogously, we have defined this. So coming to the different properties, VIID is equal to VI. So this is similar to what we have observed for an ideal gas mixture. And the entropy thing also minus R ln Xi will be coming here. And all these things are defined at a constant temperature. Now, we know this for a extensive molar property. The total M of the solution is defined as sigma Yi mole fraction into, this is partial solution, partial property N of species I in the mixture. Okay. So this mi bar, how we have derived it here, right? All the partial properties we have described here for the ideal solution. So that's why these properties of the ideal solution will be given by this sigma xivi and so on. So as we have observed in the last week session also, here xi will be always less than 1. That's why ln xi will be less than 0. So this is like a negative term, always negative. And this term is like negative, negative. So always positive. Okay. So if some solution is not um, so when we mix two different components, for example, these are there, okay. When we mix them, we can say that here entropy increases. So that is what we have seen here. The mixture entropy is greater than what it was when they were independently there. Okay. Volume is not changing ideally. Enthalpy is not changing ideally. Okay. And the Gibbs free energy also, Gibbs free energy decreases. Okay. Since it is possible that spontaneity we can say, right? Spontaneously the mixing happens, right? So that's why Gibbs energy decreases. That's how we can understand, interpret things just instead of just following the mathematical expressions. Okay. So now, since the same is there, here delta V is and delta H is 0. So upon mixing, this is less than 0 and this is greater than 0. So upon mixing, the entropy of the system is of the liquid is increasing and the Gibbs free energy is decreasing. Okay, right. So we have a Lewis Randall rule where this is like fugacity of a species sign in the mixture. Fi hat is there. Okay. In an ideal solution, ideal mixture, it is given by Xi into Fi. Ideally. Okay. Now, when it comes to non-ideality, we define excess property. This is analogous to this residual property. Okay. So now I define excess property as a difference between the actual solution value minus MID. So this MID we have discussed right now just so Xi for example if it is the M is Gibbs free energy Xi uh, minus this one, right? Okay, plus RT sigma Xi ln Xi. So that's how this is the ideal thing, but this can be something more than this or less than this. Based on that, we will be defining the excess property. And now, this M also can be expressed as sigma Xi plus RT sigma yeah. So here this is actually sigma Xi plus RT ln Xi. Okay. But instead, this has come from the thing that where we have RT VDP. Okay. VG is VDP. SGT. So at constant temperature, this is 0. So V is expressed as RT by P into dP. So this turns into uh, ln P. Okay. So that's how we are saying now as a difference Fi cap minus Xi Fi will be coming. which is defined as the activity coefficient. Okay, this is for the mixture. And this is for the ideal mixture or solution we are talking about here. So this is for the ideal solution. So this helps us to understand that ln gamma is equal to GE by RT. Sorry, ln gamma I is equal to GIE bar. Okay, that is what the mistake I have done. Yeah, so GIE bar is by RT. So this is dou NGE by RT by dou Ni at constant pressure, temperature, and Nj. Okay. So this is the thing we have. This is NMI. Right. Now, as we discussed earlier also, that if I have models for phi I, then I can get Fi. From that I get G. From that all H, B, and S, all these can be got. Right. Similarly, here this conversion thing, it is expressed here. Okay. Like that, how we can find the different properties. Now, to find this GE thing, okay, GI bar is can be found as dou NGE by dou N I. This is GI bar. So for GE, we have different models. Okay, Margulis equation, 2 suffix, 3 suffix, Van der equation, Wilson's equation, NRTL. So as I have told earlier also, different types of compounds follow different type of this model. Okay. For example, hydrocarbons follow one thing, aromatic compounds follow one thing, and alcohols one thing. Okay. Polymer kind of compounds which has a very high long chains, they follow one kind of thing. So these all depends on the geometry thing, the forces between the molecules. Okay, all these matter a lot when we are uh, trying to this is what the thermodynamics is saying here. Okay, we are trying to express different properties like the Gibbs energy, the entropy, which is completely dependent on the molecule orientations and shapes and sizes, and the internal energy, the enthalpy, okay, and the volume also. So volume also completely different depends on the forces between the molecules, right? So coming to here, the Margulis equation is defined as G by RT is equal to AX1, X2. And now we can, so generally this A is not known, right? It can be known. So I will be discussing that later. Okay. Now, if I show you G by RT equals to A X1, X2, which is A N1, n2 by n1 plus n2 whole square. Okay. I have just expanded the x1 and x2 here. Now, I want to write though. Uh, so Ng by RT equals to this n is equal to n1 plus n2, right? So, A n1 n2 by n1 plus n2. Okay. Now, so why have we converted into n1 and n2? See here, x1 and x2 have a constraint that x1 plus x2 is equal to 1. It's like if I'm changing x1, the x2 is also getting changed. This is just a mode fraction. Okay. Now, if I'm changing n1, I'm adding n1, assume. N2 is not changing. Okay. It is constant only here. So that's why I can differentiate it when I have this. For example, I want to differentiate this dou Ng by RT with respect to n1, then the all other n2 thing should be constant here. So that's why is equal to a n2 by n1 plus n2. So how do we write this? A into x2. So this is equals to ln gamma 1. So similarly, ln gamma 2 equals to a x1. And this is just a minute. Sorry, I missed one thing here. Okay. I didn't differentiate the denominator here. Okay, AX2. Okay, this is 1. Okay. Uh, this we have differentiated this N1 and plus N2. Then later minus A N1 N2 by N1 plus N2 whole square. Okay. I think this differentiation is correct now. This will give us N1 plus N2 whole square into A N2 N1 plus N2 minus A N1 N2, which is A N2 square by N1 plus N2 square. So here this is A x2 square. And this is what we have written here. And similarly, the ln gamma 2 is also given by A x1 square. Okay. Now, what is ln gamma 1 infinity? Gamma 1 at infinite dilution, which means infinite dilution means infinite dilution for species 1 implies x1 tends to 1 and x2, oh sorry, infinite dilution, right? So x1 tends to 0 and x2 tends to 1. And if I am infinite diluting for species 2, then x2 tends to 0 and x1 tends to 1. So if this is applied here, if I have gamma 1 infinity, then x2 will be 1. So that's why this is going to be A, which is written here. Okay. So infinite dilution thing is understood in that way. The similar thing can be done for the Margol's equation 3 suffix, where we have two different parameters, which is A12 and A21. Okay. Where the infinite dilution thing here for the gamma 1 for the species 1 is given by A12, and for the species 2 it is given by A21. That's why this kind of behavior is observed when at infinite dilution both show different kind of constant ln gamma. Okay, that is the difference between these two suffix and three suffix. So that is what the difference in between the Marcus equation 2 suffix and the 3 suffix. Now the one more thing is Van Laar equation, where there are A12 prime and A21 prime. These two parameters are there. Okay. And we have other models also like Wilson's equation and NRTL equation. Okay. Now coming to the thing that initially we had a like for a closed system, what will be this UHAV thing we have expressed, right? Du is equal to in terms of dp and dt, ds and dv, right? Okay, all those equations. And then later we have expressed them in like for an open system, there will be this partial molar property by dou ni will be there, okay, with changing the composition. So that is what is expressed here. Now, for the excess property, it's just a difference thing, right? So like ME is equal to M minus MID. So the same thing can be followed here also. Where now this V by RT is given by dou G by RT by dou P. Okay. This is like converted to X thing. N is converted to X. Okay, mole fraction. That is when this is expressed. And He by minus H by RT square and ln gamma is equal to. So this one. Okay, that is what I was telling it earlier. Okay. Now, here we see if I know gamma I will get G, I will get He, I will get V. So I'm completely getting the total property information. Okay. Here. Like if I know the expression clearly, then I can do this. Even if not, uh, I should be knowing the values. For example, the gamma at different temperatures and different pressures. Okay, then I can find out the HI and DI. Okay, now here the G by RT is equal to XI GI E bar. Okay, this partial property. This M is equal to sigma xi mi bar, right? This then GIE bar is by RT is expressed as ln gamma I. So now we have this GE by RT is equal to sigma xi ln gamma I. And this is a very useful equation here. Okay. Good. Now, using the Dips-Goldham equation, which we have done for the gas thing also, gas mixtures also, we have expressed this. We will be having, for example, for a binary mixture, x1 d ln gamma 1 plus x2 d ln gamma 2 equal to 0. I can write this as x1 dln gamma 1 by dx1, and right here, sorry, okay, x1 dln gamma 1 by dx1 plus x2 dln gamma 2 by dx1 equals to 0. So dln 2 by dx1 by dln gamma 1 by dx1 equals to dln gamma 2 by dln gamma 1 equals to what? Uh, minus x1 by x2. Okay. So if we know the slopes of the two graphs, so if I draw gamma 1 versus x1 and gamma 2 versus x2, then I will have the slopes here, right? That I can interpret, and then I can find out the, like, if I have one of them, then I can find out the another one. That is what I'm saying here. Okay, is it all clear? Okay. Now, this is a summary kind of thing for M and MR, which is residual property in for the gas mixture, not only mixture, pure gas also. And this excess energy is for the liquids. Okay. And you all know how this is expressed. And just now we have seen this thing, right? So V by RT and H by RT square. So that's how we get a relation between the G and V, G and S, and this G and H. Now this is Cp, which can be said the specific heat constant. Okay, dou H by dou T at P comma X. So we derive this. This is H, right? So dou H by dou T, if I say at constant P comma X, it will be coming this dou square G by dou T square at P comma X. Okay. Now, for example, if I say the CPE, if I no, okay, CPE equation, I know this is all empirical things. So if it is a constant, then and independent of T, find the expressions for GE, SE, HE as functions of temperature. So I'm just trying to uh, explain how it is working here. Suppose we have a function for CPE. Here it is a constant. Assume that. uh, So here uh, CPE is expressed as minus T into this one, right? So similarly for the excess property also, right? So this is expressed as like this. And we say this is equal to a constant, which is A here. Now, if I integrate once, I will be getting one integration constant B, and this is minus A ln T. And again, if I integrate, I'll be getting G is equal to minus A T ln T minus D plus dt plus C. This is the C is a one more integration constant. And from this G, I will be getting SC. How will be getting this minus dou G by dou T? Okay. If I differentiate this with the temperature. This one. Okay. But the negative of that. That's why we have got AL and T minus P. And then HE is represented as minus RT square into rho GE by RT. So, and P comes minus A ln T plus P. So you can see this is it is all G by dou G by dou P here. Okay. But in this case, it is dou G by RT, right? Uh, so dou NG by RT by dou T at P comma X. Okay. Right. Now I have this G. So G by RT equal to minus A ln T R and plus A by R plus B by R plus C by RT upon differentiation with respect to T, I'll be getting G minus A by RT minus C by RT square. Now multiplying it with RT, sorry, um, RT square minus RT square into this plus A T and plus C. Okay, this is what we have observed here, right? Now, the second question goes on. As for an equivalent solution, x1 is equal to 0.5 equals to x2. Okay, of benzene and n-hexane at 323.15 Kelvin. Find values for Ge, Sc, and He. Okay, at this temperature. Given the following excess property relations for an equimolar solution at 298.15 Kelvin. So we have values of these properties at some temperature. We want to know at some other different temperature. This is for like using the equations we have already derived above. So using those, I can say so Cp is equal to minus A by T is equal to minus 2.86, right? From here, I will be getting 2.86 into the temperature, that is Kelvin, 298.15. So A I will be getting, which is 852.7, right? Now, I have the He also, so I'll use this equation because I will clearly know what is C here. So 897.9 equals to 852.7, the A, into temperature, that is 298.15, plus C. Now I will get C is equal to, what is C here? Which is okay. And similarly now you have G, okay. G value is 384.5 equals to minus 852.7 into 298.15 and ln 298.15 minus 298.15 plus B into 298.15 minus 253 into 10 power 3. From here, you will get B is equal to 40. Okay. So now you have A, B, and C. And I want to find out these values at this temperature. Just substitute the A, B, C values there and the temperature values there, and you will get the values for He, Cp, sorry, Sc and G. Okay. Mm. So till now, we were discussing about some pure liquid or gas, mixture of liquid or gas. Okay. Now, liquid vapor system we will discuss. Okay. Where liquid and vapor are there, and when are they in phase equilibrium? Okay. So generally, uh, for example, mechanical equilibrium is defined when F1 is equal to F2. Forces are getting equal here. And heat equilibrium, thermal equilibrium is defined when temperatures are same. Okay. And in the between two phases, there is no mass transfer. Uh, this is the not like there is no driving force, we can say. Okay. If uh, we say, like, more fractions x1, x2 are there, then y1, y2 are there. Even if particles are moving here and there, okay, these more fractions of the species will be maintained at the equilibrium, okay, at equilibrium values of the x1, x1, y1, y2. So we are taking and talking always about binary systems because it is simpler to understand and also analytically simple. So that's why we are always talking about the binary systems. Okay. Now we have already discussed this that when a phase equilibrium is there, what is equal between them is uh, chemical potential, okay, of the liquid and the vapor is equal for both the species separately. Here, okay. Now, uh, completely this, what is mu1 dou ng by dou n1, okay. And from there you will be getting this ln gamma 1, okay. And gamma is defined as Fi by Fi ideal. So that's how we obtain that Fi, like fugacity of the species in liquid phase equals in liquid phase mixture is equal to the fugacity of the same species in the gas phase or vapor phase with a mixture. Now here the liquid fugacity is defined as Xi into gamma I into Fi liquid. Because here gamma I into Xi Fi, I can say this Xi Fi is like ideal situation. When the um, when the fugacity of the species in a mixture is given explained as the mole fraction into its own the pure species fugacity. Okay, and the in case of Fi cap vapor, similarly Phi cap vapor into YIP, and YIP is in the case of ideal gas mixture. Right now, this Fi liquid can be expressed as phi I sat pi stat into the Poynting um, factor. Okay, right? This we have discussed in the last week session. Now, on substituting all these things, we get YIP phi I vapor equals to Xi gamma I phi I sat pi sat and into exponential term. Here, phi I sat and pi sat are found at the given temperature. Now, there can be few assumptions, like at moderate pressures, the gas mixture can be assumed to follow the ideal gas mixture thing. That's why 5i vapor is assumed to be equals to 1. Now, in the right hand side, 5i sat uh, also equals to 1 at the moderate pressures. And this Poynting vector is also uh, okay. So Pi minus Pi sat tends to 0 at moderate pressures. So that's why exponential of 0 term turns out to be 1 equals to 1. That's why Poynting factor is neglected here. One more thing is that Raoult's law. Okay. Where this gamma is also assumed to be 1. So here both the gas and the liquid phase are assumed to be ideal gas and ideal solution respectively. Okay. That is what we call as Raoult's law. Generally, we say this Raoult's law is helping us to find the relation between the mole fraction of a species in the liquid phase and the mole fraction of the same species in the vapor phase. So it will allow us to establish that relationship. It's a very simple form of the thing when ideal gas and ideal solution are there. But generally, this equation is the phase equilibrium equation. Now, we will be discussing a few questions. Okay. So now we'll be discussing a few questions. The first question is, at 60 degrees Celsius, vapor pressure of methanol and water are 84 kilopascal and 19 kilopascal respectively. An aqueous solution of methanol, ethanol 1, water 2. So only an aqueous solution of methanol. This is an aqueous solution. Exerts a pressure of 39.223 kilopascal. The liquid phase and vapor phase mole fractions of methanol are x1 is equal to 0.1686 and y1 is equal to 0.5714. And the activity gamma 1 is equal to what? So we know P1 sat and P2 sat. Okay. Now we have the phase equilibrium relation, which is x1 gamma 1 is equal to y1 P P1 sat. Okay. Now we get gamma 1 is equal to y1 P by x1 P1 sat. So y1 we already know 0.5714 by x1 0.1686 into P, the total pressure 39.223 by P1 sat, which is 84.562. And this gives us 1.57. This is the gamma. Now, if you really want F1, this will be gamma into X1, F1 liquid. and we don't know this, so it's okay. This we have found. Now the second question. A methanol water vapor liquid system is at equilibrium at 60 degrees and 60 kilopascals. Uh, the mole fraction of methanol in liquid is 0.5 and in vapor is 0.8. Vapor pressure of methanol and at this much temperature is P1 sat is given and P2 sat is also given. Assuming vapor phase to be an ideal gas mixture, so in this relation x1 gamma 1 P1 sat is equal to y1p. So here, as we discussed earlier, both the ideal gas and ideal solution, the gamma 1 is equal to 1. So here what is written, assuming vapor phase to be an ideal gas mixture. So this is ideal gas and this is non-ideal solution. So from here, the question is, what is the activity coefficient of water in the liquid phase? So this is for the water, okay? Gamma 2 is equal to Y2P by X2 P2 sat. Therefore, gamma 2 equals to Y2 is 0.2 and X2 is 0.5. Okay. And P is 60. P2 sat is 20 kilopascal. Now this is equal to 1.2. And the second question is, what is the excess Gibbs energy of the liquid mixture? So we know we have a relation G by RT is equal to sigma xi ln gamma I. So equal to x1 ln gamma 1 plus x2 ln gamma 2. Here x1 equals to x2 is equal to 0.5. So it's equal to 0.5. We have found that gamma 2 is equal to 1.2. So ln gamma 2 I will take. And similarly, we want to find gamma 1 also, which is equal to 0.8 by 0.5 into 60 by 85, which gives us 1.13. So that's why this gives us 0.1523. Now we have G is equal to 0.1523 into 8.314 into 273 plus 60. So this is the temperature in Kelvin. And this will be giving us 421.6 joule per mole. This one. And here it was this one for the water. Okay. Now, moving to the third question. At 318 Kelvin, uh, and at a and at a total pressure of 24.4 kilopascal, the composition of the system, ethanol and toluene at equilibrium, x1 equals to 0.3 and gamma 1 is equal to 0.634. The saturation pressure at a given temperature for pure components is given. P1 sat is known, P2 sat is known. Now, we want to calculate the liquid phase activity coefficient. So, the same thing we are following x1 gamma 1 P1 sat is equal to y1 P. And we know the total pressure also, which is 24.4 kilopascal. So, what do you want? Gamma 1 is not known. So, gamma 1 is YIP by X by PI sat. So, uh, sorry, this is Y1. Now, gamma is not known. 0.634 into 24.4 by x1 is 0.3 into P1 sat, which is 23.08. And this will be giving us gamma 1 is equal to 2.23. And similarly, gamma 2 equals to 1.26 meters. Just a minute. Now, value of the G by RT of the liquid phase. So, G by RT equals to sigma xi ln gamma is to 0.3 ln 2.3 plus 0.7 ln 1.269. So this gives us 0.407. Okay. The question is a reasonably general expression for vapor liquid phase equilibrium at low to moderate pressures is phi I YIP into is equal to xi gamma I fi naught. This fi naught is the fugacity of the pure species, where phi I is vapor fugacity coefficient, gamma is the liquid activity coefficient, and Fi is the fugacity of pure component I. The Ki value is therefore in general a function of what? So we have phi I Yi P equals to gamma I Xi and phi naught. If I write it in terms of Yi is equal to KIP, we'll get gamma I Fi naught y phi I P into x1. Here, if I express this as yi is equal to ki into xi, where ki equals to gamma phi naught by phi I into p. Here, phi naught depends on phi I sat, vi sat, vil, p, r, rp is there, not term p. So it depends on everything. It depends on these PVT. Okay. The one more term is gamma 1. So this depends on like the ln inverse or exponential g by rt. And generally, we have models, right? Margulis, Van Laar. So what all are these expressed in terms of? Is expressed in terms of composition, right? Ax1, x2. So this is depending on composition, right? So therefore, this depends on C. Okay. So this gamma is represented only in terms of x1 and x2. So yi it is not dependent. Okay. Fine. So we understand that the system is not a linear system. Okay. Yi is equal to ki xi. So this ki needs to be changing based on the xi also, keeping the yi constant, right? The fifth question is a binary liquid mixture is in equilibrium with its vapor at a temperature of 300 Kelvin. The liquid mole fraction X1 of species 1 is 0.4 and the molar excess Gibbs free energy is molar. Okay. So T is equal to 300 Kelvin. X1 is equal to 0.4 and the molar excess gets free energy. So this is my partial, okay? So G equals to 200 joules per mole. The value of the R is given. We are gamma I denotes the liquid phase activity coefficient of species. So if ln gamma 1 is equal to 0.09, what is the value of ln gamma 2? So there is one plus point when we are discussing the binary mixtures. We have this property, right? So G by G is 200. So this is already known 0.09. So now this is what is unknown. And from it we can calculate easily that what is ln gamma 2 is equal to 0.0735. Okay, there is one more question. For a binary mixture at constant temperature and pressure, which one of the following relations between activity coefficient and mole fraction Xi is thermodynamically consistent? Thermodynamically consistent, uh, we have ln gamma 1 and ln gamma 2. So consistent relation should be in between these only. So for a binary mixture, we have already looked into the thing that sigma xi d ln gamma I equals to 0, right? So that's how we have written that x1 d ln gamma 1 plus x2 d ln gamma 2 equals to 0. And I can write this as x1 d ln gamma 1 by dx1 plus x2 d ln gamma 2 by dx2 equals to 0. Now I can see among all these options the ln gamma 1 is same and I want to find what is ln gamma 2. So now I will do this term d ln gamma 1 by dx1 equals to 0 plus 2 minus 2x1. Or I can write 2 into 1 minus x1. Now I can express from here as d ln gamma 2 by dx1 equals to minus x1 into d ln gamma 1 by dx1 by x2. equal to minus x1 by x2 into, so this is 1 minus x1 is actually 2x2. Okay, here, right? Into 2x2 equals to minus 2x1. Now on integration, I should be writing dln gamma 2 equals to minus 2x1 dx1. On integration, I'll be getting ln gamma 2 equals to minus x1 square. So this one. Okay. So this is how easy it is. So if you know just one equation ln gamma 1 also, you can find out what is ln gamma 2 using the relations we have here. Okay. Next question. Molar excess Gibbs free energy of a liquid mixture A and B is given by this equation. Okay. Where XA and XB are the mole fractions of A and B respectively, and so and so. Okay. C1 and C2 are temperature dependent parameters at 300 Kelvin. C1 is 0.45 and C2 is minus 0.018. If gamma A and gamma B are the activity coefficients, the value of this. So instant reaction after seeing this, people will be going like ln gamma A minus ln gamma B. So I will find this by doing dou Ng by RT by dou N1 and this with dou N2. But this is a very lengthy process. Of course, you will get the answer through it. But smarter way to relate to this is you have a relation in terms of xi, okay? dGe by RT equals to ln gamma A by dx1 gamma A by gamma. So this is a proved, can be mathematically proved, okay? Proved relation, okay? Now, if I want to integrate this, I will say ln gamma A by gamma B dx1 equals to d of g by integration of g by RT. And I'll get this is from x1 is equal to 0 to x1 is equal to 1. And here this will also be when x1 is equal to 0 to x1 is equal to 1. Because anyway, this is a function of the x1. So this is what we want to find, right? This LHS. So RHS is equal to uh, So here you can write xp as 1 minus x everywhere. Okay. Then if you substitute, you will be getting 0.036 minus 0.504 plus 0.468 plus to 0. Right? Hence, therefore, so at these values of C1 and C2, it is equal to 0. Next question is the Van Laar activity coefficient model for a binary mixture is given by this form. Now, what are the values of A star and B star? We have to find out. So, given gamma 1 is equal to 1.4. Okay. Now, okay, we can do somewhat manipulation mathematically. Now I have ln gamma 1 is equal to A star by B star x2 plus A star x1 whole square, and this denominator here will go to numerator. So B star square x2 square. So this is AB square x2 square, but by this, okay. Now from this equation, ln gamma 2 equals to, the denominator is remaining same, unknown. Like, yeah, A star x1 plus B star x2 square into B star into A star x1 square. Now, what do I want is, see in this equation, this is the term depending on the composition and all. So if I know this term, okay, then I can find A star because I already know the gamma 1, right? So that's why ln gamma 1 by ln gamma 2, I am dividing both these, is AB square x2 square by BA square x1 square. So B by A x2 by x1 whole square, okay? Or else I can write x1 so x1 ln gamma 1 by x2 ln gamma 2 equals to B by A x2 by x1. So this is what the term is. Okay, the ulta of that is here and the same b by a x2 into x1. So now I have it in terms of x1, gamma 1, x2, gamma 2, which all of which are known here. Now I will substitute that here. Ln gamma 1. Okay. I will directly write it in terms like a star equals to ln gamma 1 into 1 plus x1 ln gamma 1 by x2 ln gamma 2 whole square. This whole square. So, and b star equals to ln gamma 2 into 1 plus x2 ln gamma 2 by x1 ln gamma 1 whole square. And using this, I will get a star is equal to 3, b star is equal to 0.5. Okay, of course, if it's a like competitive exam, you can go for simpler way. Okay, you just substitute one of them and do the trial and error for all of them. Okay. Next question is a binary liquid mixture consists of two species, 1 and 2. And okay, using a molar excess Gibbs free energy model, gamma ln gamma 1 versus x1 are plotted. Okay. Similarly, ln gamma 2 versus. So with respect to x1, they are plotted. A tangent drawn to the ln. So here there is a slope. The tangent slope equals to minus 1.7 to 8. And we know x1 is equal to the slope is at x1 is equal to 0.2. So what is slope of tangent? d ln gamma 2 by tx1 at x1 is equal to 0.2, right? Then as we have this already, x1 d ln gamma 1 by dx1 plus x2 d ln gamma 2 by dx1 equals to 0. Hence, this one, what we require, equals to minus x1 by x2 d ln gamma 1 by dx1. x1 is minus 0.2, and x2 is 1 minus 0.2. So 0.8 into minus 1.728. So this will be positive and equal to 0.432 slope. Okay. Next question is mole fraction and activity coefficient of component 1 in a binary liquid mixture are x1 and gamma 1 respectively. So these excess monomer R is which one of the following is always 2. Okay. So here everything we can see limit x1 tends to 1. Okay. So as x1 tends to 1, gamma 1 is going to f1 cap by f1 id. So what is ideal? It is x1 liquid. X1 not, right? So as x1 tends to 1, only one of the species is present. So that's why f1 cap by fy naught is equal to 1. Both are same. Okay. Then gamma 1 is equal to 1. Therefore, ln gamma 1 is equal to 0. Now what we have is G by RT is equal to sigma xi ln gamma I. And since x2 is 0, we have only x1 ln gamma 1. And this tends to 0 from this, right, is equal to G by RT is equal to 0. So, first option. Okay. And a binary mixture of components 1 and 2 form an azeotrope at 130 degrees. And x1 is equal to 0.3. So, azeotrope says us x1 is equal to y1 and x2 is equal to y2. We know x1 is equal to 0.3. Therefore, x2 is equal to 0.7. Okay. And then same y1 is equal to 0.3. y2 is equal to 0.7. The liquid phase non-ideality is described by ln gamma 1 equals to a x2 square. So this is a Mg2 suffix. Okay. So the fugacity coefficients are 0.9 at the so phi1 equals to phi2 equals to 0.9. Saturated vapor pressures are given. P1 sat is equal to 70. P2 sat is equal to 30. The total pressure, so P equals to what? So we know x1 gamma 1 P1 sat I, okay, I you consider xi equals to yi P into phi I cap. Okay. Now you want to know P is equal to x1 gamma 1 P1 sat by y1 phi 1 cap. Equals to x1 I already know 0.3 into gamma 1. So gamma 1 I don't know. So ln gamma 1 equals to a into x2 square. But I don't know what is a. So first I will aim to the so let this be here. We'll first look into how to find the a here. So if I come up with this, like gamma 2 by gamma 1, here if I compare from this I get from this equation, gamma 1 is equal to y1 p phi 1 cap by x1 p1 sat. So here these both are equal in azeotrope case. And Okay. And gamma 2 is similarly y2 by x2 p phi 2 cap p2 sum. So gamma 1 by gamma 2, I will be getting phi 1 cap by phi 2 cap, which are actually equal. P by P cancel. So P2 sat by P1 sat I will get. Okay. So I have their ratio 70 by 30. Gamma 2 is generally, so here ln gamma 2 is equal to ax1 square, right? So I will be representing as exponential of ax1 square by exponential of ax2 square equal to 7 by 3. Therefore, exponential of a x1 square minus x2 square plus to 7 by 3. I already know x1 is equal to 0.3, right? Next to is equal to 0.7. On substituting and solving this, we will be getting a equals to minus 2.1182. Okay. So I have the a now. So going back to this equation, p is equal to x1 gamma 1 p1 sat, but by y1 phi 1 cap is equal to 0.3 into minus 2.1182 into p1 sat. P1 sat is 70 by y1 is 0.3 into phi 1 cap, which is 0.9. Sorry, this is A, right? Sorry, this is okay. Sorry, yeah. So now I will calculate gamma 1 is going to exponential ax2 square, and I found that equal to 0.65. On calculation, I will get it as 27.55. Okay. So these all questions we have on this show. So as a part of this, actually, there is a set of questions where um, you will have either the one of the temperature or the pressure of a system, and you will have one of the mole fraction of gas or liquid, and then you can you with the set of equations we have, we solve them and find the mm, bubble temperature or dew temperature, or the other way, bubble pressure or dew pressure. So I actually want to explain you people by using MATLAB code for solving. Uh, there is actually 6 equations, solving them with the given input. So I want to take an extra session for that. Or maybe I'll include that along with this week 9 session, because this it is related to the week 10, right? Week 10 syllabus. So I will be adding it to this video. Okay. Thank you.